A Tesla valve, or as Tesla called it a valvular conduit, is invented by Nikola Tesla in 1920. It allows a fluid to flow preferentially in one direction, without any moving parts. That's why Tesla called it valvular conduit, because it's like a conduit with no moving parts. However, the geometry inside this conduit is the interesting part. As we said, this is a valve without any moving part. So how it works? Let us see that. Here is a cross-section of Tesla valve. Let us first consider right to left flow process or forward direction. The design of the valve allows fluid to flow unimpeded in this direction. As we all know, the fluid takes the easiest path. So in our case here, most of the fluid follows the main path, with very minor flows following this unnecessary direction that also has no obstacles, so it again joins the main fluid stream, leading to a fluid leaving the valve with the same entered flow. In this flow direction, the flow is very smooth, and the valve acts like a pipe where only surface friction should be considered. Now let us consider left to right flow process or reverse direction. Here the structure of the valve plays the major role. A Tesla valve consists of a series of 11 flow control segments placed in series with the direction of the fluid flow. Each flow control segment consists of a slight deviation from the straight line path from source to target, and a divider which leads to a bucket. The more flow control segments, the more restricted the valve. In our conduit here, we have 9 flow control segments. Although any other number of such segments could be used as desired to increase or decrease the flow regulation effect. One computational fluid dynamics simulation of Tesla valves with 2 and 4 segments showed that the flow resistance in the blocking or reverse direction was about 15 and 40 times greater, respectively, than the unimpeded or forward direction. Here what happens in this undesired direction. Primary flow and secondary flow are more evenly divided. Primary flow is almost undeviated from a straight line path. It follows a gentle zigzag from source to target. On the other side, secondary flow loses velocity as it reaches the bucket at the end of the flow control segment. Secondary flow is reversed almost 180 degrees and pushed back into the path of the primary flow, but in the opposite direction. Vortices and turbulence are formed where the secondary flow rejoins the primary flow, further restricting progress. This happens again at every control segment, restricting the flow again and again. Finally, let us differentiate between one-way valve and Tesla valve. A one-way valve requires the restriction of fluid flow from some source to some target in an undesired direction, while not restricting the flow in the desired direction, where the source and target are switched. The Tesla valve does not entirely obstruct fluid flow in one direction, however, so it is not a foolproof system. The Tesla valve is used in microfluidic applications and offers advantages such as scalability, durability, and ease of fabrication in a variety of materials. But its usage is limited in other applications because it is not a perfect blocker. Thank you for your time, and do not forget to subscribe for more interesting videos from AMJ Engineering.